We're delighted to be here this morning to tell you about our work in detecting pre-symptomatic cognitive change. That is, cognitive change sufficiently subtle that it's not even noticed by the patient and is typically not followed up on by the clinician. We have technology for detecting this accurately based in part on careful use of analytics. Let me give you an overview of where the talk is going by spilling the punchlines from the very beginning. First, we are indeed accurately detecting cognitive change in patients that look normal on existing screening tests. That matters because cognitive change is a worldwide problem with a $1 trillion price tag associated with it. The essence of our test is to infer cognitive state from novel features of subtle motion using analytics, which makes it significantly more sensitive than existing tests. An important point is that early detection of a disease enables fundamental change in cognitive evaluation. We'll show you how that comes about. And early detection also offers the potential for significant efficiencies in medical practice and, as we'll show you, enormous cost savings. And then Dr. Rudin will come up and talk to you about our machine learning methods work, which shows that we can produce classifiers that provide both accuracy and understandability. Now, our task arises ironically out of good news. The good news is we're all living longer. Around the world, populations are graying. The less good news is that we're living long enough to confront cognitive decline. For example, in the US, more than 5 million people have been diagnosed with Alzheimer's disease. Their care costs more than $200 billion a year. And if nothing changes, the demographics are such that by 2050, the number of cases in the US is likely to triple, with costs that are estimated at over $1 trillion a year. That's just in the US. The estimation is that worldwide, there will be 135 million cases of Alzheimer's by 2050 if nothing changes. It's not surprising then that some people refer to this as the Alzheimer's time bomb. Someday, there'll be a pill that stops Alzheimer's in its tracks, perhaps even one that cures it. But there isn't one yet. The best we can do at the moment is early detection, because if we can detect a disease like this early, we can begin treating it, and that can slow down the progression of the disease, giving us precious time. Early detection is a key. One approach to early detection is to look for what's called biomarkers. These are proteins in your body which are thought to indicate the presence of the disease when they are present in high volume. Here's a chart from the Alzheimer's Association showing some of those biomarkers. It's a little bit of a complicated chart, let me explain. Along the x-axis, we have the progression of both time and the disease from normal to what's called preclinical state, to MCI, which is mild cognitive impairment, and then finally dementia, perhaps of the Alzheimer's type. The y-axis goes from normal to abnormal. But what I wanted you to pay attention to is the first 4 curves and the conditions under which they're measured. You'll see that it says PET, a PET scan, MRI, an MRI scan. These scans cost thousands of dollars each. It also refers here to CSF, cerebral spinal fluid. Do you know how you get cerebral spinal fluid? Some people are nodding. It's a spinal tap. It's a really nasty experience. Okay, it can make you sick for several days. So all 4 of these much beloved early markers come from tests that are either very expensive, invasive, or both. Now let me call your attention to this curve here, the purple one, cognition. The good news about cognition is we can measure it in ways that are neither invasive nor expensive. The less good news is it's out here on this part of the chart because the current technology for measuring cognition is sufficiently crude that in order to be judged cognitively impaired, you have to score 1.5 standard deviations below normal. You have to be at the 7% level to be judged impaired. If this were cardiology, that would be the rough equivalent of saying, we figured out there might be something wrong with your heart because you just had a major heart attack. We want to do better than that, okay? So we want to get this early. In particular, our work is involved in coming up with cognitive tests that are not out here, but are in fact back at this stage, detecting early when there's cognitive impairment, and as a consequence, making it possible to treat early. Because if we can detect early, We can treat early. That allows us to slow the progression of symptoms. That, of course, has enormous medical, sociological, economic consequences. I don't know if any of you have had experience in your friends or family with Alzheimer's disease, but the advanced stages of the disease require round-the-clock custodial care. They are astonishingly expensive. So that's the good news about early identification. Another good part of early identification is if we can pick out people who are early in the disease process, then we can help out the process of developing methods for treating dementia at a much earlier stage. If the drug companies can get a supply of people who are known to be much earlier in the disease state than they normally get them, then they can focus on developing drugs that are good at that stage. So then, how are we going to get early detection? We started with a well-known test. It's called the clock drawing test. And it's deceptively simple. The physician gives you a sheet of paper and a pen, and the instructions are simply draw a clock showing 10 minutes after 11. This is called the command clock because you do it on command. Then they give you a second, and you might draw something like this. Then they give you a second sheet of paper with a pre-drawn clock on it and say, please copy this. Technically, that's known as the copy clock. And as simple as this test is, consider the cleverness. The first half of the test and the second half actually test slightly different cognitive properties. The first half of the test requires that you understand the language, envision what a clock looks like, do all of that work. The second half is about spatial perception and planning, so it's quite cleverly designed to test different parts of your cognitive function. Now, the kinds of results you see on the test may look like, a little hard to see, but there's a clock there with no hands. Here's a clock with even more stuff left out. Here's a clock where the planning didn't go very well, and sometimes people repeat themselves, sometimes quite extensively. Now, it's obvious that there's something wrong if you see a clock like this. Most of the cases are far more subtle, as we'll see in a moment, but you can see examples like this sometimes. The good news about the clock drawing test is it's fast, easy, non-invasive, and cheap, paper and pencil. It's also widely accepted. It's been in use for more than 50 years. There's a lot of experience with it. GPs use it, neurologists use it, it's used in laboratories and so forth. The less good news is that it's insufficiently sensitive at the moment, hence it's only used if the patient is already overtly impaired. It's also labor and time intensive to score, and because some aspects of the scoring are subjective, it's not particularly reliable in both scoring and interpretation. But for us, the most fundamental flaw is that it focuses on output alone. It focuses on the finished drawing, not the process by which the drawing was done. And we believe focusing on process gives an enormous amount of additional information. Here's an example we use to try and illustrate that point. And you guys are the wrong audience for this. We typically show this to clinicians, and the question is, does either of these clocks show sign of cognitive impairment? I'm not going to ask you, okay? But the answer is, by the way, they look pretty normal, don't they? I mean, at least that much you can tell, all right? Even being laypersons, we can tell they look pretty normal. It turns out that the one on the right, in fact, has hidden impairments, and our software is capable of uncovering those hidden impairments, and as a consequence, is far more sensitive than any test currently available. So let's turn to our test, which we call the digital clock drawing test. We do this by having people take the ordinary clock drawing test, but using this technology. It's a digitizing ballpoint pen. In the patient's hand, it feels like an ordinary ballpoint pen. You can draw with it. It leaves behind ink. But intriguingly, it also measures its position on the page 75 times a second to within 2/1000ths of an inch. It's actually strikingly accurate in both its timing and position measurement. Some of you may be familiar with the technology. It works because there's actually a camera in the barrel of the pen that looks down on the paper, and the paper has been imprinted with a very faint dot pattern, and the software in the pen figures out where it is on the page from moment to moment by what part of the dot pattern it can see. And importantly, I want to stress this again, the pen feels perfectly normal to somebody using it. It's just a ballpoint pen as far as the patient is concerned. This is important because we want to capture absolutely natural behavior of people. People don't think twice about writing. They do it all the time, and that gives us a good measure of how they're actually performing. Now, a decade of research with this test has accumulated a large database of both normal and pathological behaviors for us to use as a baseline for analysis. We've accumulated 5,300 tests, over 4,200 different individuals. Our healthy individuals, by the way, are a stratified sample of a normal population. And there are 8 other sites that are using this research, using this technology for the research, both in the US and abroad. The basic idea, as I've suggested, is that micro movements of the hand while you're drawing reveal subtle behaviors that are indicative of pre-symptomatic cognitive change. Here's a quick view of the system in operation. I'm just going to show you a few snapshots of it. Here's one of the clocks you saw earlier. When I press this button down here at the lower right, a collection of artificial intelligence techniques derived from our work in sketch understanding are used to classify each of the pen strokes. Which one is the hand, which one is the one, what's the clock circle. And when that classification has been done, the system color codes the display just so it's really easy to see what it decided. So our process starts with descriptive analytics, starting with automated sketch interpretation. The results of that sketch interpretation are shown colorfully in the display. The next step is to compute hundreds of features about the strokes in both of the clocks. We compute the obvious sort of geometric features, the height and width and angle for all sorts of things. But importantly, we also compute process features as well. So we look at the order in which things are happening. And as you'll see in a few minutes, we compute latencies, the delays in things. And those delays turn out to be very interesting information. Because our measurements are defined in code, they are, of course, objective, repeatable, virtually instantaneous, with no user effort involved. And because we preserve the raw data that came from the pen, anytime we think of a new feature that we want, we can simply write the code for that and compute it for that test, even if the test had been taken a decade earlier. And we had done this. We have tests from a decade ago, and we've come up with new things we want to measure over the years, and we say, okay, we can measure that. There's no need to go back and retest. We've got new information about that patient. Now let me show you some of the value in analyzing process as well as product. I'm going to show you a movie of sorts, except this isn't a video. This is a reproduction of the patient's actions done by simply playing back the point-to-point pen movements. So we're playing back the pen movements from the raw data. Here it is being drawn. When there's a pause here, there's nothing wrong with the movie. That's the patient pausing. I want you to pay special attention starting now. Watch, 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 watch. Ah, okay. Now, all of you notice that the patient paused for approximately 5.973 seconds, right? Come on, you're OR types. You caught that? Okay. No, of course you didn't. No one ever does, but we get that because of the data we're collecting. We know exactly how long that pause was. Now, some pause before starting to draw the hands is absolutely normal. You're task shifting. You're going from one cognitive task to another. The normal time for doing this is around 2 seconds, which we know from all of our data. This patient paused for almost 6 seconds. That's not normal. And you can't see that in the final drawing. So by attending to process, we pick up things about people's behavior. That's a key insight. And in fact, I'll come back to this later, we call this pre-first-hand latency, and it has interesting diagnostic consequences. Here's another clock. Not obvious what's going on down at the 6th position, is it? Once again, let me simply play back the pen data and watch. Notice the patient got mentally stuck. Drew a 12, drew another 12, noticed what was going on, fixed it by drawing over it. Okay? We'd never have the ability to figure that out if all we had was the final result. So process is a big benefit. Now, there's lots of other features to these clocks. Let me zoom in on just one more and literally zoom in. I'm going to zoom in on the 11 here. And you'll notice if I make it big enough, it becomes clear that there's a little hook at the bottom of the 11. We have a technical term for it. We call it a hooklet. Why is it there? It's there, we think, because the patient is thinking about where they're going next before they've completely picked the pen up off the paper. Thinking about what you're going to do next is a sign of cognitive health. If you're impaired, all you can do is think about what you're doing at the moment. Okay? So the ability to have a hooklet here, the presence of a hooklet, but by the way, completely unconscious. Nobody says, I'm going to do this. It's a natural part of your ordinary behavior. We think the disappearance of hooklets will be one of the earliest signs of cognitive impairment. Something you don't even know you're doing, and we can capture it. By the way, there are times when nobody else knows that you're doing it either, because I've blown this up to the point where it's obvious. But if I show you a scale, I know this is a little bit hard to see, but this is 1 millimeter, which means that hooklet is under a ½ millimeter long, which means if you look at the physical ink, you can't see it in the physical ink. But it's picked up by the electronic ink and automatically detected by our software. Now, let me show you how this works at the doctor's office. You know, when you go into the doctor's office, typically it starts off with getting your temperature taken, your blood pressure, and ordinary standard measurements called intake, the standard kind of intake. This test will be part of that intake, administered by a nurse or a staff member. Once the test is done, by the way, it takes about 2 minutes. The pen is docked. The moment the pen is docked, the data is transferred to a server. The moment it lands on the server, it's analyzed, and within about 3 minutes, we have a detailed report that's available. The office staff can get this report with any ordinary web browser. They can add it to the electronic medical record or print it out and put it in the patient's file. Notice that the physician has spent 0 time on this so far, and by the time they see the patient, there's additional important information, that they've got. Here's what the hardware in the office looks like. There's the pen at the top. There's the dock for the pen. And this is the computer. It's about the size of a paperback book. That's all we need. And its only job is to get the data from the pen and transmit it over the net to the server. It is completely independent of any other computer equipment in the doctor's office. There's no need to install software on any existing machine. This operates independently to get us the data that we need. Now with that, let me show you some of our early clinical results. Because we know exactly when the pen is in contact with the paper, we know when the patient is writing and when they're not. So we've come up with 2 measures. One we call think time, the other ink time. Ink time is when you're drawing, think time is when you're not drawing. There are some interesting results from this. It turns out that even in normal patients, 60% of the time spent taking the clock test is spent thinking rather than inking, which means 2/3 of your effort involved in that test has not previously been analyzed. Total thinking time also turns out to have diagnostic consequences. In particular, it differentiates early Alzheimer's, the tall green bars, from these other classes, including normals, AMCI, amnestic, mild cognitive impairment, and others. So total thinking time, something that simple, can be diagnostic. Earlier, we saw the notion of pre-first-hand latency. And it turns out that command clock pre-first-hand latency differentiates amnestic MCI from amnestic MCI and depressed from early stage Alzheimer's, while the copy clock pre-first-hand latency differentiates amnestic MCI and depressed from early Alzheimer's. This matters because distinguishing Alzheimer's from AMCI and depression is an important and recurring clinical question. It turns out even pen speed all by itself has diagnostic consequences. Just looking at the pen, the speed of the pen as they draw the clock circle, here's the speed at each quarter of the clock circle, has diagnostic power. Pen speed differentiates groups along the continuum from normal older folks to those with amnestic mild cognitive impairment to Alzheimer's disease. Finally, and perhaps most intriguingly, one of our colleagues, Dr. Kate Price at the University of Florida, who does some very interesting work in imaging, is using our technology as well, and she's discovered that some of the measures are correlated with brain structure. So, for example, in healthy controls, think time is negatively correlated with parietal thickness. Here's the parietal area of the brain. And that matters because parietal thinning is associated with early Alzheimer's disease. She also looked at those with Parkinson's disease and discovered that think time is negatively correlated with thalamic volume. Here's the thalamus. And that matters because smaller thalamic volumes are associated with neurodegenerative disorders. Now, our focus so far is on Alzheimer's and other forms of dementia and Parkinson's, but we believe our technology is much more broadly applicable than that. It's applicable to measuring and monitoring cognitive state in many different circumstances, and is applicable across the lifespan, from teenagers to centenarians, and across cultures because of the ubiquity of a simple clock face. We've begun exploring its applicability to a wide range of other conditions as well. And with that background, I'm going to ask my colleague, Dr. Cynthia Rudin, to step up and talk about our work in machine learning.
All right.
It's okay. Sorry.
All right, thank you, Randy. So I'm going to talk about machine learning, and in particular, the way that predictive power trades off with the transparency of the way the clock drawing test is scored. Now, there are two important tasks, screening and diagnosis. In the screening tasks, we determine whether someone reasonably could have a condition. And in the diagnosis tasks, we have to figure out which condition they have. And we're considering three types of conditions, so memory impairment disorders like Alzheimer's disease and amnestic MCI, vascular cognitive impairment disorders like forms of dementia that are vascular-based, and then Parkinson's disease. And in our academic papers, we go into a lot of detail about all the screening tasks and all the diagnosis tasks, and in much more detail than I'm able to here. So I'm going to focus on the screening tasks today. So how accurate is the clock drawing test for screening for cognitive impairments? Well, doctors have developed their own ways of scoring the clock drawing test, and they evaluate the quality of their scoring using the area under the ROC curve, or the AUC, which is a classic measure of the quality of a predictive model. And as it turns out, the AUCs reported in the literature for the physician-generated scoring systems range from 0.66 to 0.79. And 0.5 is random guessing, and 1 is perfect. And so that's a pretty big range there. And part of the reason for that range is because there are inter-rater reliability issues where you can have multiple doctors looking at the same test and scoring it completely differently. Now, we are trying to design our own scoring systems for the clock drawing test, and we want to compare it to what a doctor would have scored, the same test. So we've got to find ways to automate scoring, physician scoring, for large numbers of tests. And the most pragmatic way to do that is to operationalize the scoring systems, meaning we have to turn the English instructions for the doctors into executable code. So let me tell you about that. Now, this is one of the doctor scoring systems. This was designed by Dr. Rouleau, and she has designated a maximum of 10 points per clock drawing test. And 2 of the points are for the integrity of the clock face, whether it's distorted. And then there are 4 points dedicated to the presence and sequencing of the numbers around the clock. And then there's another 4 points dedicated to the presence and placement of the hands of the clock. And you'll notice the vague English terms like gross distortion and some distortion. We've got to define these things precisely. So for us, we're going to measure distortion of the clock face by the eccentricity of an ellipse that has been fitted to the clock face. And this is something that Randy discussed. So for us, no distortion means the eccentricity is below a threshold. And we can optimize this threshold, to make the whole scoring system as accurate as possible. So here's another example. No representation of size difference between the hands. So for that, we're actually going to be using the ratio of the sizes of the hands. Okay, so this is the full operationalization of the Rouleau test. And as you can see, all the terms are very precise, things like eccentricity and hand ratio and so on. And now, since we have this, the tests can be scored automatically. There are no more inter-rater reliability issues. and they're no longer subjective. Now, we not only operationalize the Rouleau test that I just showed you, but we also operationalize these 6 other widely used scoring systems for the clock drawing test. And all of the parameters were optimized, so that makes the performance optimal. So this is arguably better than what's done in practice. And it's certainly more consistent because now it is no longer subjective. Okay, so how do the operationalizations perform on our data set? And how do they compare with the physician scoring systems that I mentioned ranged in the literature between 0.66 and 0.79? And the answer is here. So the variance has narrowed, and you'd expect that because now we're working with a single data set and we have no more inter-rater reliability issues. But it's definitely within the range of what's been published. Now, everything I'm going to present from now on, I'm going to fill in this table, and all of this is new. This is old, this is new. All right, so now that we know how an operationalized doctor might perform on our data set, let's use machine learning, because this is naturally a machine learning problem. So in accordance with good practice, we apply many machine learning techniques, the arsenal of machine learning weapons. We have decision trees, C4.5 and CART, ensemble methods, boosting and random forest. We have optimization-based approaches like support vector machines and regularized logistic regression. We use standard techniques for tuning the parameters, nested cross-validation. And all of the results that I'm presenting are out-of-sample results because I'm using cross-validation. Okay, so how did the machine learning techniques fare on our data set? And the answer is here. So remember, one is perfect, and we are upwards of 0.93. Now, in terms of prediction performance, this is excellent. But what I was hoping to do is something that would be kind of better than both the machine learning and the operationalizations, right? The machine learning has good predictive power. The operationalizations are what doctors are used to. They're transparent. So hopefully we can do something that is sort of the best of both worlds. All right, so for that we need new machine learning techniques. So I'm going to talk about 3 types of algorithms. The standard machine learning toolbox that I just discussed, and 2 new methods. Supersparse linear integer models, or SLIM, and Bayesian rule lists. And these 2 algorithms are designed for interpretable machine learning. We're also going to try 2 different sets of features. I just presented results for all of the features. We're also restricting our attention to a subset of the features called the Clinician features, which are just the ones that are used in existing scoring systems. So we call these Clinician features. For example, no gross distortion of the clock circle that I showed you in the Rouleau test. Now, all features includes all of the special features from the digital pen, all the timing information. All right, so you should expect to see 6 sets of results, 2 by 3. The first one I can show you is the machine learning results on the Clinician features, and that's here. So as you can see, we do lose substantial accuracy by throwing away the features from the digital pen. So again, this is throwing away all the timing information. However, you will notice that this is substantially more accurate than the operationalizations, right, of what the doctors do. And remember, the Clinician features are using this. The Clinician features are the same as what are used in the operationalizations, but the machine learning methods are more accurate. All right, now, my expertise is in machine learning, and the issue that I always have with machine learning techniques is that they produce these black box models. These models are very complicated relationships between input and output, and you can't put them on a PowerPoint slide, and you can't even understand exactly what they're doing because the computation is so complicated. And they're unfamiliar. They don't look like the scoring systems that doctors and patients are really used to. And so they might not be useful in practice. Now, I don't want us in the field of machine learning to have what I call the problem of Cassandra, where we produce these beautifully accurate predictive models and then nobody uses them and nobody trusts them because they can't understand them. So what if we could produce a machine learning model that does look like an existing scoring system? A model that's linear, it adds things together. Something that's sparse, it has only a few non-zero coefficients. The coefficients are integer, like 3 points for this, 2 points for this, 5 points for that. And then favoring more interpretable features. Because, among two equally good predictive models, we'd like the one that's more interpretable. We'd like a model that looks like physicians created it, but was actually created from data. And so that is the goal of supersparse linear integer models. And it's a mixed integer linear programming-based algorithm for sparse linear models with integer coefficients. So here's the notation for SLIM. The xi is the feature vector for patient i's clock test, and yi is the label, whether or not the patient has the disease for screening. And then yi hat is our prediction. It's the sign of a linear model with coefficients lambda. And we want the predictions to be as close to the truth as much as possible, but we also want lambda to consist of interpretable values. So SLIM has an objective that consists of two terms, one for accuracy and the other for interpretability. This is a soft interpretability constraint, and then this is a hard interpretability constraint. So for example, if you want them to be integers, then you set this L set to be the set of integers. So let's talk about the loss function. And that is actually just a combination of false negatives and false positives. And you want the user to be able to trade off between those two things because for certain tasks, one is more important than the other. And then let's talk about the soft interpretability penalty. And that is comprised of two terms. A classical sparsity penalty, which is an L0 semi-norm that counts the number of non-zero coefficients. And then an understandability penalty that's comprised of two terms, where these terms are actually interesting. The first of them penalizes for non-zero coefficients the complexity of the feature. And the complexity of the feature comes from a hierarchy, where the top of the hierarchy is more interpretable and the bottom is less interpretable. So here's an example where total time to draw both clocks would be considered more interpretable than total time to draw either one of the two separate clocks. And then the other term is an L1 norm, and usually L1 norms are used for sparsity, but here we have an L0 norm. And actually, I can prove that if epsilon is below a particular value that I can compute, then this actually cannot interfere with sparsity. So what is that term for? And the answer is coprimeness. It actually, all it does is make the coefficients coprime. So if you have these coefficients, it would turn that into this, and it would remove all of the common factors. So here's the notation for SLIM. You have the, I don't want to go too much into detail about this, but you have true positives, false positives, and the soft interpretability penalty. That's comprised of the three terms, the sparsity term, the complexity term on the features, and the coprimeness term. So here's a result. It's a SLIM model for memory impairment screening. And it predicts that someone has a memory impairment disorder if their score is less than 10. And you get points for things like having all the digits be present and so on and so forth. You have points for the hour hand being present, and then you lose points for things if, like, you cross out digits or you take a really long time to draw it, or your minute hand points to the wrong place. And the thing I like about this is that it's just as interpretable as like the Rouleau scoring system or the other scoring systems, but it was created from data. And SLIM has a lot of theory that's associated with it. It has probabilistic error bounds on its out-of-sample prediction quality, and because it uses coprime coefficients, we're able to use concepts like Fairy numbers from number theory to make those bounds tighter. We also derived that if the parameters are within a certain range, we lose no training accuracy for using integer coefficients. And we have data reduction bounds where we can solve a series of convex optimization problems and remove large parts of the data and provably get the same solution. SLIM also has other applications. This is a paper on sleep apnea screening, and this is on recidivism prediction for prisoners. So here's how SLIM performs. And again, you're losing some accuracy over the standard machine learning, but what you gain is interpretability, because these models are interpretable like these models, but they're much more accurate. And then if you restrict to the clinician features, again, you lose accuracy. But even the worst SLIM performance here is better than the best operationalization. And again, these models are using the same features as these, and they're just as interpretable. So let's talk about Bayesian rule lists. Bayesian rule lists produces logical models that are comprised of if-then rules. And they are a competitor for CART, which is classification and regression trees. CART is probably the most widely used predictive modeling method in industry right now. We have 3 papers on Bayesian rule lists, and each of them has won a Best Paper Award in the last year. And BRL optimizes this complicated-looking function, which is actually the posterior of a Bayesian model, hierarchical model. And it uses a series of theoretical bounds and cutting to produce cutting planes. And then also, we use a lot of systems-level techniques to do some of the logical bit vector manipulations. And it runs very fast. And it's not like CART. CART has no global optimization at all. It's local heuristics. So here's a Bayesian rule list for memory impairment screening. So this model was completely produced from the data by Bayesian rule lists. And it says if the command clock minute hand points to the wrong place, then there's a 94% chance you have a memory impairment disorder. And then if that is not true and your digits look okay, then there's only a 16% chance. If you took a really long time to draw it, there's a 92% chance, and so on. And here's Bayesian rule list performance using all of the features. Again, the difference between these and these are that the models are interpretable. And then here's Bayesian rule list for the clinician features. So that's about all the results that I wanted to present here. The summary is that we now have accurate objective scoring systems for the clock drawing test. We have the operationalizations that we did not have before. We have the machine learning methods producing very accurate predictive models. And we also have the new transparent models that are machine learning models for transparent modeling. They outperform existing systems, and they consistently produce AUCs above 0.8, particularly when we can use the special features from the digital pen. I like this project because it is a good example of a centaur, which is a human-machine combination that can perform better than either humans or machines alone. So it's producing knowledge that's in the same language as what physicians are used to, but more accurate. And hopefully that will ease barriers to adoption. All right, and our machine learning paper contains a lot more detailed experiments. We have ROC curves for all of the screening tasks, diagnosis tasks for all the algorithms with uncertainty bands, additional subsets of features that we've considered, and also some important correlations and associations that haven't been seen before. So here you go, Randy. Okay, all right.
Thank you, Cynthia. Let me go back to my slides to just have a few final comments. Okay, what I'd like to do is summarize and take a little look forward at where we're going next with this work. One thing we're doing is to design new drawing tests. We have come up with a novel version of a maze test that's giving us very interesting information, in particular information about real-time decision-making, because we can track the speed of the pen as you approach a decision point. So we can watch you slow down or stop or come to a skidding halt. Very interesting information there. We're also looking at a broader category of movements. Drawing is, of course, a purposeful kind of movement. We're also looking at tremor, which is not a purposeful form of movement. Somewhat more broadly, we've considered the possibility that we might be able to help out with fitness assessments in people in high-risk jobs like surgeons and pilots. This is very speculative, but it's an interesting possibility. And for SLIM, we're looking at the ability to generate probabilistic outputs and to handle regression problems. For BRL, we're developing methods to determine whether a rule set is in fact the optimal one, which would give it the same reach toward optimality as already exists in SLIM. So, let me summarize a few things. First, this technology enables a fundamental change in cognitive evaluation. People use compensatory strategies, and they do it without even noticing it. We all, it turns out, find ourselves when we get older. We find ourselves slipping, and we find ways to deal with it, like keeping lists and writing notes. But our tests can see through those strategies by detecting subtle behaviors that reveal the effort hidden behind the result. As a consequence, we can now think about assessment differently. We don't have to wait until people look impaired. Instead, we can detect people working harder and thinking longer for the same result. This is key, because most testing these days is results-based. We can detect the effort that went into the result, and as a consequence, we have a much more sensitive measure. So if you want a sort of one-sentence summary of why we think we can do better, there's a part of it. The technology we've been talking about here that's been developed over 10 years has just recently been leased to a startup company called Digital Cognition Technologies. It's in the process of trying to get FDA approval as a screening tool, wants to work with major pharma, and would eventually like to see this in every doctor's office. The important point is we would like to see this transition out into the real world because we think it works and because we think it can save lives. Let me summarize our work on analytics. Our descriptive analytics involve the use of sketch interpretation technology to identify pen strokes, and then the computation of an extensive set of features, importantly about both product and process. The predictive and prescriptive analytics involve the super-sparse linear integer models that Cynthia was talking about, the Bayesian rule lists, as well as operationalizing the existing scoring systems and optimizing them for accuracy. And if you look in our paper, you'll see we have a detailed quantitative study that Cynthia sort of hinted at that shows you the transparency, accuracy trade-off. And we think that's an interesting and important result as well. Okay, let me summarize. The problem we're working on is enormous and looming and will affect all of us to some degree. And when you've got $1 trillion problem, even a very small improvement can add up to several dollars. We believe our technology is a game changer because we no longer have to wait for impairment to manifest. We can detect it while it's still in the subtle stages, and we have a 2-minute test that saves physician time and effort, making the physicians that much more efficient and making the test results that much more accurate. We believe our technology offers the possibility of early detection, something of enormous value because, as suggested earlier, if you can detect early, you can treat early, which slows down the progress of the disease, which has enormous consequences, both in financial and emotional costs. And if any of you have had the unfortunate experience of having some experience with Alzheimer's in family or friends, you can imagine the emotional value of just a few more years with somebody while they still know who they are. Thank you.